right, guys, at home, can I get a thumbs up that you hear me and see the board okay? Awesome. All right, so I'm starting, technically, this is obviously the third day that we've been working on 6.1, but it took us 2 days to get through what should have been our first day just because of the shortened periods. So these are your day 2 notes. I'm not even going to finish these ones today because it just takes too much time. And I really don't want to rush. Oh, my head say, what am I doing? I don't want to rush this. Yep. Okay. And then good news is I didn't even make a new homework for tonight because we're not really going to get through a lot of substantial problems today. I'll just put the couple problems that we get through at the end on tomorrow's homework when I hope we finish section 6.1, all right? But no new homework today. I just want to show you some really important things. All right, so yesterday we were introduced to radians. It's a very, very important way to measure an angle. Basically, it's measuring an angle by the length of an arc, and then depending on how many radiuses fit into the length of that arc. That's how an angle gets measured in radians. So the angle is measured as a real number. So we're going to be able to label a coordinate plane with an x-axis in radians because the input to a trig function is an angle. So we're going to be able to put that input on the x-axis as an angle in radians, all right? All right, so what did we learn? We know that in one complete rotation or revolution in a circle, there's 360 degrees. And then we saw yesterday that one complete rotation or revolution around the circle is equal to 2 pi radians. So every circle will have about 6.28 radii that fit around the outside. And for every radius that fits on the outside, there's an angle the size of 1 radian on the inside. So every circle consists of about 6.28 radians living inside of it, okay? All right, so again, the way we're measuring an angle in radians is you have a radius, you have an arc, and then you have an angle that is formed by that arc. This angle is measured depending on the length of this arc, S, and then how many radiuses can fit along the length of that arc. So divided by R. So that's how we measure an angle in radians. We see how many radiuses fit inside the length of that arc. So S over R. So when theta is measured in radians, the length of the arc has been divided by the radius. Okay, well guys, when we're working with the trig functions, there are going to be special angles that we come across, the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. So 30, 60, and 45, and any multiple of them, those are going to be really, really important angles for us because they can all be equated to the side lengths of a right triangle that we can memorize. These are all angles that we're going to have trig ratios that we can find the exact ratio for it because we can memorize the side lengths to these 30, 60, 90 and these 45, 45, 90 right triangles. So I want you to become very familiar with what 30, 45, and 60 look like in their radian measurement and then what multiples of those angles look like in their radian measurement. Because when you come across these angles, you have to know their trig ratios inside and out. You have to be able to find them without a calculator, okay? So here we go. So degrees is on top, and then radians is on bottom. So we have 0 degrees, that's 0 radians. 30 degrees is pi over 6 radians, because guys, remember, when you're looking at an angle in radians, pi represents 180 degrees. What's 180 divided by 6? It's 30. It's 30 degrees. So this is what 30 degrees looks like as a radian measurement. Pi over 6 is going to be an extremely important measurement for you. 45 degrees is pi over 4 radians, okay? If you took 180 and divided it by 4, that's 45. So pi over 4 is an extremely important radian measurement. 60 degrees in radians is pi over 3. 180 divided by 3 is 60 degrees. So pi over 3 is something that when you see it, you're like, oh, that's 60. I got it. I'm with you. All right? 90 degrees, which isn't inside a quadrant. It's one of our quadrantals. It's right on the positive y-axis. 180 divided by 2, that's pi over 2 radians. So that's another really important measurement that when you see pi over 2, you got to be like, oh, that's my 90 degree. I know pi over 2, all right? All right, now we're going to start getting into some multiples, all right? Well, I'll come back to that. The other important one is pi. We know 180 degrees is pi radians. That's one of our conversion factors, okay? Then we have some more multiples, and then we have 2 pi is 360 degrees. Those are the major ones that you guys have to know, inside and out. When you see pi over 3, 60. When you see pi over 6, 30. When you see pi over 4, 45. You need to know these radian measurements. All right, so now, after you get done, everything else is either a multiple of a 30-degree angle, it's a multiple of a 60-degree angle, or it's a multiple of a 45-degree angle. So you'll start seeing 2 pi over 3, 3 pi over 4, 5 pi over 6. You need to start recognizing them as, oh, it's one of my special angles. And this is how I recognize them. Guys, this is 2 pi over 3, right? Pi over 3. Wait a minute, pi over 3, that was our 60-degree angle. 2 pi over 3 is 2 60-degree angles. It's 120. So start recognizing the pi over 3 first, and then say to yourself, oh, there's 2 of them. So that's 2 60-degree angles. When you see 3 pi over 4, recognize the pi over 4 first. And be like, oh, that's a 45. That's 3 45-degree angles. That's 135 degrees. I'm telling you, it's much easier to think of them that way. 5 pi over 6. Recognize the pi over 6 first as, oh, that's my 30. This is 5 30-degree angles. It's 150. So I feel like it's like, oh, this isn't that bad, as long as you can recognize your pi over 6, your pi over 3, and your pi over 4. All right, and then where's the other one? Look here. 3 pi over 2. Recognize that as, wait, that's pi over 2. That's my 90. That's 3 90-degree angles. That's 270. So really start thinking of them as how many 30s, how many 45s, how many 60-degree angles. Because I'm telling you, these are radian measurements that are going to pop up all the time, and they just expect you guys to know what their sines, their cosines, their tangents are going to be without using your calculator. Because all of these are multiples of one of our special angles, and we can memorize the side lengths to a special right triangle. All right, they start asking you what's like, 2 pi over 9. That's not one of our special angles. That's not a 30, that's not a 60, that's not a 45. That doesn't live inside of one of our special right triangles. That's not something we should be able to memorize, but these ones are. So all of these measurements, they apply to the unit circle. You guys have heard of the unit circle, the talk of it? Yes, have you seen it? I'm not sure. So the unit circle is something that pre-calculus and calculus, they rely on to help you guys memorize these special ratios for these special angles. That's all the unit circle does. Everyone's like, oh, we're going to do the unit circle this year, right? I've heard of the unit circle. Guys, at the end of the day, it's a memorizing tool. It literally just helps you know these ratios for these special angles. All the answers are on the unit circle. So this is what the unit circle is going to look like. I just want to start filling these angles, these special angles, into their place on the unit circle. That's all I want to do is just start showing you where these angles land. We're not going to put their ratios in yet, but we're going to start showing you where the angles fall on the unit circle. Because I'm telling you, every year I have students, they're like, I love the unit circle because it has every answer you're ever going to need on it. So if you can construct one really quickly, it's like, wow, this is like literally a cheating tool. And it is. All right. All right, so let's remember, we have special angles, right? These are the big dogs, 30, 45, and 60. 30 degrees is pi over 6. 45 degrees is pi over 4. 60 degrees is pi over 3, right? 180 divided by 6, 180 divided by 4, 180 divided by 3. Nice and easy to memorize. Okay, where do they fall on our circle, and where do their multiples fall? And how will I remember? Wait a minute, where was 5 pi over 6? Where was 11 or 5 pi over 3? You should know where they land on the circle, because the quadrants play a huge role in knowing their ratios sign, whether it's positive or negative. All right, so guys, let's do this first. Let me show you degrees, and then we'll fill in the radians. And again, this is not like, you're not going to have homework on this. It's just, it's important to know this. All right, so here is 0 degrees, right on the positive x-axis. Then we have our first special would be 30 degrees. That's a 30-degree angle. Then we have our next special, which would be 45 degrees. Cuts the quadrant 1 right in half. and then we have 60 degrees. All right, and then we got our 90 degree up here. So now once you hit 90 degrees, now we're just gonna start doing multiples of our 30s and 45s and 60s, which all of your 60s are just a multiple of the 30, so there's a lot of overlap. All right, so 90, we go another 30 degrees, that's 120 degrees. All right, and then from 90, another 45 degrees is 135. And then from 90, another 60 degrees is 150 degrees. And then halfway around the circle, here's our 180 degrees. All right, then we go another 30 degrees and we get 210. Then we go another 45 degrees and we get 225 degrees. And then we go another 60 and we get 240 degrees. And then from 180, a full 90 degrees away from him, there's our 270 degrees. 270 with another 30, there's 300 degrees. 270, another 45 degrees is going to be 315 degrees. And then 270, another 60, there's our 330 degrees. And then one more 30 brings us home. 360 degrees lands in the exact same spot as 0. Because again, this is why these are periodic functions. Once you make one complete rotation, now 390 degrees lands in the same spot as 30. So we're going to be able to apply all of 390 degrees ratios to 30. Okay. Oh no. Oh no. Hold on. Sorry, my pump just expired. That's all right, we're fine. I can change it when I get home. All right, here we go. So that's what degrees looks like. So degrees, like I said, we're nice and comfortable with degrees. It's the radians that we have to get used to. So this is how I advise you in the future when you're asked, hey, what's the sign of 4 pi over 3? And you're like, holy crap, what's 4 pi over 3? Where is that? Where does it land? What's its reference angle? Is it a 30? Is it a 60? Is it a 45? What quadrant is it in? This is how you'll easily be able to figure out where is 4 pi over 3. All right. So, like I said, all of these are multiples of 30, 60, 45, right? Well, guys, I'm going to count it off. I'm going to skip the 45s. I'm just going to do your 30s and 60s right now. This is your first 30-degree angle. This is your second 30-degree angle. This is your third 30, your fourth 30, your fifth, your sixth, your seventh, your eighth, your ninth 30-degree angle, your 10th, your 11th, and your 12th. So 12 30-degree angles bring you all the way around the circle. So that's how I'm going to have you label your radian measurements. We're going to count it off by pi's over 6. 1 30-degree angle, 2 30 degrees, 3 30 degrees, and you'll see all the measurements in radians carry over. All right, so guys, right here, this is our first 30-degree angle. So it's already written there. It's 1 pi over 6. Okay, this is your second 30-degree angle. So it's your 2 pi over 6. Guys, what is 2 pi over 6 reduced to? It's pi over 3. I'm not going to reduce until the end, though. I just want us to count it off. All right, this is your third pi over 6. You know what? I'll reduce it now. What is 3 pi over 6 reduced to? Pi over 2. 90 degrees is pi over 2. 180 divided by 2, there's your 90. So we're just counting it off. That was our third. Here's our fourth 30-degree angle. What is 4 pi over 6 reduced to? 2 pi over 3. Guys, 120 degrees is 2 60-degree angles. It's 2 pi's over 3. Remember, we're skipping our 45s. That was our fourth. Here's our fifth pi over 6. So 5 pi over 6 lands in quadrant 2. All right, this is our sixth 30-degree angle. What is 6 pi over 6 reduced to? It's pi. That's pi radians, halfway around the circle. All right, we go to our next 30. This is our seventh 30-degree angle, our 7 pi over 6. Go to our next one. This is our eighth 30-degree angle. What is 8 pi over 6 reduced to? 4 pi over 3. And guys, think about it. 4 pi over 3 is 4 60-degree angles. 4 times 60, that's 240 degrees. That's exactly where it should be. All right, this is our ninth 30-degree angle. 9 pi over 6, what is 9 pi over 6 reduced to? That's 3 pi over 2. It's your third 90-degree angle. It's 270 degrees. All right, here is our 10th pi over 6. Our 10th 30th degree angle, 10 pi over 6 reduces to 5 pi over 3. It's your fifth 60th. 5 times 60, 300 degrees, right there. All right, we go to our 11th 30-degree angle. That's 11 pi over 6. It's already written there for you in that quadrant. And then bring it on home. This is our 12th pi over 6. What is 12 pi over 6 reduced to? Boom, 2 pi radians all the way around. So that's how you can very easily figure out in the future when you're dealing with 7 pi over 6 or 5 pi over 3. Where the hell is that angle? Guys, it's just a count. You can count it all. All right, now let's do our 45s, and you'll know where all of these special angles land. Because like I said, their landing, their placement is going to be crucial in the future. What quadrant are they in? All right, so here is 0 radians. Here is our first 45-degree angle. It's 2 pi over 4. I'm sorry, 1 pi over 4. All right, our second 45-degree angle is actually right here. But guys, what is 2 pi over 4 reduced to? Pi over 2. We already got that right. All right, here is your third 45-degree angle, so that's 3 pi over 4. Here is your fourth 45-degree angle, 4 pi over 4. What's 4 pi over 4? Pi. It's pi radians. Here is your fifth 45-degree angle, 5 pi over 4. Here is your sixth pi over 4, your sixth 45-degree angle, and guess what it reduces to? 3 pi over 2, 3/90. And then here is your seventh 45-degree angle, 7 pi over 4. And then last, bring it on home. Here's your eighth 45-degree angle, your 8 pi over 4. What's it reduced to? 2 pi. So again, right now you can be like, dude, what's this lady up there doing right now? But I'm telling you, in the future, you're going to be asked to find the sines, cosines, and tangents of any one of these special angles from memorization. And guys, they're not all positive ratios. We're on the coordinate plane. Some of them are going to be negative ratios, and the quadrants play a huge part in that. So it's important to understand where these angles land. Go ahead, Michael. Yeah, absolutely. Okay. All right, are you guys okay? Have you seen and filled this in before? So it actually makes sense. Awesome. All right, here we go. Let's try a few sector problems, and then I'm going to have to let you guys get out of here. All right?
Is the calculator needed for these problems?
Actually, no.
Oh, okay.
These are quite simple.
I was like, should I run it over?
I don't think you'll need it. All right, this is how we find the area of a sector. The sector of a circle is bounded by a central angle. So you got a central angle. It's bounded by that and the intercepted arc. So basically, it's just a chunk of the circle. It is a fractional portion of that circle. The area of a sector is therefore a fractional portion of the circle's entire area. For example, if the radius is 4 and the central angle is 45, then what is the area of that sector? So guys, think about it. You have the area of a circle, which is pi r squared, but it's not the entire area of the circle. It's just a fractional portion of it. So what fractional portion of it depends on, well, how many degrees out of the total degrees make up this sector, if you will. So in this case, it would be what degree out of 360 degrees, that's going to be the fractional portion of your area times pi r squared. So to find this one, they're telling you the angle is 45 degrees and the radius is 4. So that means, well, what's the fractional portion of our circle? We have 45 degrees out of 360, which reduces to 1/8. So you're going to have 1/8 of the area of this circle. So that's going to be 1/8 of pi r squared. It's only 1/8 of the entire area. So plug in your radius and you'll find your area. So 1/8 of pi 4 squared is going to be 1/8 pi times 16. Well, 16 divided by 8 is 2. That's 2 pi. So the area is 2 pi, whatever unit the radius is measured in, feet, inches, centimeters, it's some type of unit squared. And that would be the exact area, otherwise the area is 6.28. And again, it has nothing to do with the amount of radians living inside the circle, it's just by chance, that's the area of this sector. All right, so again, it's a fractional portion. So the area will equal of your sector whatever the angle is in degrees out of 360 times pi r squared. Now, if your angle is measured in radians, the book will argue that it's easier to find the area because the formula gets simplified. So guys, if your angle was in radians, right, then you would have, it's going to be theta radians out of 2 pi radians, that's the fractional portion of the circle you'll have, times pi r squared. But in radians, this pi and that pi cancel, and you're just left with the area equaling. Basically, it's theta times r squared divided by 2, but they pull the 1/2 out and say 1/2 times theta times r squared. So that would be the formula you would use if your angle was in radians. But guys, to tell you the truth, I don't even go off the formulas. I just take my angle over 360 times pi r squared, or I take my angle over 2 pi times pi r squared. It's just a fractional portion of the area. And to me, that's easier to memorize. But you do what you got to do. All right, so guys, look here. Find the area of a sector of a circle who has a radius of 5 feet formed by an angle of 40 degrees. And they say to round to 2 decimals, so we won't leave it in its exact measurement. The book is going to say convert your degrees to radians. But why? I don't see the point. My area is literally going to be, I have 40 degrees out of 360. That's the fractional portion I'm going to have, times pi r squared. So really, it's 1/9 times pi times, what's my radius here? 5. I don't feel like I need to spend time converting my angle to radians and chancing even getting that wrong when the formula is easier either way. So now I'm going to get 25 pi over 9. And what is this? This is feet squared is what the radius is measured in. So to me, I have no problem doing it in degrees. I can literally easily figure that out. And then 25 times pi divided by 9, I wrote this down, is about 8.73 that we would round it to. All right. So again, just to show you, if you took your 40 degrees and you converted it to radians, right, you'd get 40 pi over 180, and it becomes 2 pi over 9. So now, in radians, the formula said the area will equal 1/2 theta r squared. So it's going to be 1/2 times 2 pi over 9 times 5 squared. The 2's cancel. It's 25 pi over 9. So either way you do it, whether the angle is in radians or degrees, to me, one isn't easier than the other. I would actually argue I don't want to take the time to convert to radians to do this. So then you would still get the exact same answer that you got in degrees. So it's your call. Do you want to change to radians? Do you not want to change to radians? The formula works either way. Now again, you end up getting some ugly angle that's not 40. Maybe it is easier in radians. But right now, I don't see the need to switch. All right, why don't you guys try this one, and then obviously we're gonna be done for the day. Now again, 30 degrees, you should know automatically what that is in radians, so there's nothing to convert. You could easily say, oh, that's pi over 6, and you could go right to the 1/2 theta r squared. So again, the formula is definitely simpler when the angle is in radians. So since 30 degrees is such an easy angle to convert to radians, we know it's pi over 6, then yeah, I might go right to my 1/2 theta r squared formula for when the angle is measured in radians. And then it's 1/2 times pi over 6 times 2 squared, since the radius is 2. 4 pi over 12, that's pi over 3 feet squared, which is roughly 1.05. All right, but if you just did it as 30 out of 60 times pi r squared, it's the exact same answer. So you decide whether you like degrees or radians. I'm never gonna pick one for you. Does that make sense? Everybody okay with that? Okay, so again, everybody at home, thumbs up, we're okay? I'm not giving homework on anything today. Just finish the homework that is due tonight. There's homework due tomorrow, and I'll put these couple sector problems on our homework for tomorrow night, okay? All right, and again, I don't mean to bore you with things you already know. It's just these are so important. These angles, we need to know who they are, okay? All right, have a great day, guys. I will see you guys tomorrow.